Hi everyone, this is Mr. Bowman, and in this last video for Chapter 12, we are going to talk about finding lines of best fit for nonlinear data. I know that sounds like an oxymoron, but what we're going to do first is we're going to figure out various ways to linearize the data and then use that to come up with a least squares regression line in terms of the linearized variables. So in this case, we're looking at the relationship between the length of a fish caught and its weight. And what we'd like to do is we'd like to start out by making a scatter plot of length versus weight. So I am going to zoom in on this so you can see this data, and why don't you pause the video for a moment and enter length in for your explanatory variable and weight for your response variable, and take a look at that scatter plot and then describe that in terms of the acronym that we used, FODS, form, outlier, direction, and strength in context. Alright, so as you can see, we've got a nonlinear set of data here. And as the length of the fish increases, so does the weight. The association is curved, positive, and a strong association. In the next question, it says, do you think that a linear model is the best fit for this data? Clearly, that's not the case because this data is not linear. So then the question becomes, well, what would be the most appropriate model? And it's often helpful to look both at a scatter plot of the data itself and think about the context. Some people might look at this and think, oh, this is exponential growth, but it also looks like it is approaching the y-axis as x approaches 0, which kind of makes sense. As the length of the fish approaches 0, its weight's going to approach 0, which would mean that's not, or probably not, an exponential relationship. You can think about the context of the problem to help you with this as well. In part C, it says, consider the relationship between the length and weight for the fish data. Does it seem reasonable that the weight of the fish is a function of the volume of the fish? Well, yeah, actually it does, because weight is a function of volume, and volume is basically 3 dimensions, and length is 1, so maybe there's a cubic relationship there. So if you think about graphing an untransformed cubic function, it lies in the first and the third quadrant. We would clearly only be interested in it in the first quadrant, and question D asks you to sketch a graph of a cubic. Could the pattern and scatter plot be modeled by such a function? It could, actually, if we only use the data in the first quadrant of a graph of a cubic, which is where our data lies. So if you have any idea what kind of relationship it is, you have to start thinking about how you might want to transform the data. And if the data is a cubic relationship, in other words, volume is, the weight is related to the cube of the length, if we wanted to straighten that out, we could take the cube root of one of the variables. The question then would become, well, which one should we take the cube root of? And in this case, it makes sense to take the cube root of the weight, because we would think the weight would be some cubic relation of the length. So what we're going to do is we're going to take the cube root of the weight and plot that versus the length. So in your calculator, you should have the data in there ready. I happen to have the data in lists 3 and 4, and in list 3, I have the length. In list 4, I have the weight. So what I'm going to do is I'm going to put my cursor over here on list 5, which is empty. Make sure you put the cursor on the list name, and I'm going to take the cube root of the weight, which I have in list 4. And so for me, I am going to say, let's take list 4 and raise it to the 1/3 power. And that generates the cube root of the weight for us. Now what we're going to do is we're going to plot on the x-axis the length, and on the y-axis the cube root of the weight, and see if that linearized the data. So we go up to our scatter plot and we make sure we've got a scatter plot turned on, and we make sure we pick the right lists. So for me, this would be list 4 and list 6, and then hit zoom 9, and oops, I have some sort of error here. So let's me figure out what I have going on here. So I'm going to go back to my stat plots and see what I've got going on. List 4, list 6, list 4, list 3, list 5 is what I really wanted to do. So list 3, list 5. And we'll try that again, zoom 9. And as you can see, that did a great job of linearizing the data, which tells us that we do truly have something very close to a cubic relationship here. So what do we do next? We fit a line to this data. So we would do stat, calc, linear regression, item 4 or 8, doesn't matter, but make sure you pick the lists that have the transform data. So list 3 is the length, and list 5 is the cube root of the length. Frequency list is blank. We're going to store the regression equation in Y1, and we're going to go ahead and calculate this, and we now have this line of best fit. You can see the values for R and R squared are very close to 1. We're going to graph this and see if it fits our scatter plot of the transformed data, and it does. Let's pull that back up one more time, and let's go back and take a look at the questions that we're asked to answer here. So, find the least squares regression line in the residual plot for this transformed data. You could do that on your calculator and see that you have a slope of 0.247 and a y-intercept of negative 0.022. Don't forget, we took the cube root of the weight, so when you write your regression equation, make sure you say the cube root of the weight. Technically speaking, this should be the predicted cube root of the weight there. R squared is 0.998. And if you're asked to interpret R squared in context, make sure that you think about the transformed data. So, R squared, the coefficient of determination in this case, tells us that 99.8% of the variation in the cube root of the weight, the response variable, from the average cube root of the weight can be predicted by the least squares regression line. The next part asks you to describe the residual plot. I am going to leave that up to you to verify that the residual plot is random with no clear patterns, which means it was appropriate to fit a line to the transformed data. From a user's point of view, nobody really wants to know the cube root of the weight, so typically you would be asked to solve for the response variable. So in this case, you'd have to cube both sides, and when you did that, you would get the predicted weight is equal to 0.247 times the length minus 0.022, whole thing cubed. And you could check and see that it fits the original data. So if you were to go back to the original data, the length and the weight data that was curved, and you were to plot this function, you would see that it would fit it particularly well. I will leave that up to you. A typical question then would ask you to use your equation to predict the weight of a fish that has a length of a certain length. So you'd plug that in and you'd come up with a prediction. You can also do that by using the value function on your calculator as long as that length is within the range of values that you have in your window. So this approach to linearizing data is great, but if you don't have any idea of what the relationship is, like you may not have had for this particular example, you could try an infinite number of transformations to figure this out. You could have taken the square root of the weight, or the weight, instead of to the 1/3 power, you could take it to the 1/3.5 power, and so on and so forth. So there are some other ways that we can approach this to try and linearize this data, and we're going to start out by looking at the log of the length versus the weight and the log of the length versus the log of the weight. So what I want you to do is I want you to pause the video and experiment with those. So in other words, just to be clear, if you go back to your data here, and we're going to get rid of the cube root of the weight, clear that out, and let's say I want to take the log of the length. Okay, that's log of list 3. You can use whatever log base you want, natural log, log base 10, log base whatever. Just for convenience sake, I am going to take the common log or log base 10. So log of what's in list 3 and hit enter, and then we're going to plot that versus what's in list 4. So experiment with that, see what works, and then unpause the video and we will continue. So what you found is that the most effective at linearizing the data is the log of the weight versus the log of the length. And if we did that, our least squares regression equation would be log weight, or predicted log weight, is equal to 3.05 times the log of the length minus 1.90 with an r-squared value of 0.998. And if we were to interpret that r-squared value, we would say 99.8% of the variation in the log of the weight can be predicted by this least squares regression line. And if you look at the scatter plot, it's random with a little bit of increase in the magnitude of the residuals as the length increases. Again, you'd be expected to solve for the weight. Nobody wants to use a prediction equation that tells them the log of the weight. So if you're doing this, inverse of log base 10 is exponential base 10. So you take 10 to the power of both sides, and you get something that simplifies to this. I want you to take a minute and take a look at this, pause the video if you have to, and think about the algebra that's going on here, because you absolutely have to know how to do this, and we will go over it in class. So what you notice here is that the final equation that we get is the predicted weight is equal to 0.0126 times the length to the 3.05 power, which helps to make the point that nobody would have guessed that that would have been the power relationship that we would have had. Most people would have guessed to the third power, but to the 3.05, okay, it works better. So what can we do instead of experimenting? We can try those transformations that we tried using logs. So we can take the log of x versus y. We can take log x, log y, plot that, or we can take x versus log y. And the chances are one of those is going to linearize the data. If taking the log of x and plotting y versus log x linearizes the data, you have a logarithmic relationship. If plotting x versus log y transforms the data to be linear, then you have an exponential relationship. And if it requires you to take log x and log y, then you have a power relationship like the example that we did. Now, what follows here is just a justification of how x log y results in an exponential function and log x log y results in a power function. So we will go over this in class if anybody has any questions, but essentially what we're doing here is we're finding a line of best fit in terms of log y and x, and we're solving for y. And in doing so, you'll get an exponential relationship. On the other side, we're finding a linear equation in terms of log y and log x, and we're solving for y, and in doing so, you'll get a power relationship like the example that we had. So how should you approach these problems? Well, if you know or you've been told or that the relationship is quadratic, for example, or a power of degree 3 or power of degree 4, then you should think about taking roots, for example. Or what you can always do is you can resort to this approach here, which will work for pretty much any situation that we're going to run into. So if you want to pause the video and give that a try, here's an example of some data using distance for x and the revolution time for the planets to go around the sun for y. Try and linearize that data using the approaches that we came up with, and then unpause the video and look at the solutions. So in this case, if you use log x versus log y, or natural log x versus natural log y, that would give you the best linearization of that data. Y, r was closest to 1, r squared was closest to 1, the scatter plot was linear, the residual plot showed the least amount of pattern, the standard deviation of the residuals was the smallest. Those are all great indications that you have the best transformation. Very often these problems are dealt with on the AP exam using computer output. So for our fish data, you will see transformation 1 is the length cubed. Notice that they cubed the length this time instead of the cube root of the weight. And transformation 2, they took the cube root of the weight. So you can take a look at those two and you can find the lines of best fit, and you can find the values for r and r squared. And it appears that both of those are very good fits. What I do want to point out to you is that you have to think about S in context if you're interpreting it. So in the first set of transformed data, S is 18.8, which seems very, very large, but that is the average error in predicting the weight. In the second set of transformed data, S is 0.124, which is the average error in predicting the cube root of the weight. The other thing you have to do is to make sure you take a look at the residual plot. And here are the two residual plots for these two sets of data. And both of them actually look reasonably good. Remember, you should be able to find the least squares regression lines for the transformed data off the computer output. Make sure you pay attention to using the length cubed in transformation 1 and the cube root of the weight in transformation 2. And then be able to justify which model is the best. In this case, both models appear to be very good. High values for r squared, random pattern on the residuals. R squared is a little bit higher for the second model, and S is lower even after taking into consideration the cube root for the first model. Therefore, if you had to pick, transformation 2 is maybe slightly a little better than transformation 1. But that's basically the idea about linearizing data. If you want a little bit more practice, move on to this last problem here. And this is about Moore's law. Some of you may be familiar with that. And after you're done, you can unpause the video and take a look at the solutions. So as you can see, the scatter plot shows a nonlinear pattern. If you take the log of the response variable, the log of the y values, it does a pretty good job of straightening it out. So if that's the case, then what that indicates is you have an exponential relationship. In the next part, there's the Minitab output for the transformed data. And it says, does the computer output below also suggest a linear model is appropriate for the transformed data? And yes, because r squared is high, S is relatively small, so the average error in the predicted natural log of the transistors is about 0.5. This is small in comparison to the range of the predicted values from about 8 to 22 on the scatter plot with the natural log of the transistors. So if we use that, we have the following equation. The predicted natural log of the transistors is equal to about 0.37 times the years since 1970 plus approximately 7. And you can use that to predict the number of transistors on an Intel computer chip in the year 2020. You could also be asked to interpret the S value in the context of the problem, which we talked about just a minute ago. Don't forget to take a look at the residual plot. There is some pattern in this residual plot, so it would raise some concern for me as to whether or not a linear model is appropriate for this transformed data.